Afternoon, sir.
Good morning.
Good morning,
Morning,
sir.
sir.
Okay, so can you see the
Morning, sir.
blackboard? Good morning.
Yes, sir.
Okay, so have you got the link of live recorded lectures and this PPT and the PDF file?
Yes, sir.
Okay,
Yes, sir.
okay. So मैं वहाँ अपडेट करता रहूंगा अब सारी चीज, ठीक है? वो लिंक को आप रेगुलरली चेक करते रहना। ये इसका जो XPS फाइल है, ये जो भी ब्लैक बोर्ड पे जो हम कर रहे हैं उसका XPS फाइल एज इट इज वहां पे है, तो वो अपडेट होता रहेगा। जो भी आगे का कंटेंट आएगा तो पुराना फाइल नए से रिप्लेस हो जाएगा। एंड वीडियो लेक्चर्स एक्स्ट्रा ऐड होते रहेंगे। एंड पीपीटी भी है। पीपीटी में ऑलमोस्ट जिनर डायोड तक कवर किया है, तो पीपीटी में ऑलमोस्ट बहुत आगे तक लेक्चर तक कंटेंट है। तो यू हैव नाउ ऑल द दिस मटेरियल्स फ्रॉम माय साइड। बुक भी मैंने शेयर कर दिया था। Okay, so now we will see the remaining topics, 6 students. Okay. Okay, so now I have to mute you guys, and if you have some doubt in any point, you can raise your hand and you can ask. Okay. So आखिरी के 5-6 मिनट हम स्पेशली डाउट के लिए रखेंगे, ताकि एक लेक्चर का फ्लो बना रहे, और फिर आपको कोई 5-6 मिनट में डाउट्स आते हैं इन केस, तो फिर हम उसको एड्रेस कर लेंगे। So, okay. Waiting room admit all. Okay, so can you see the blackboard? Is the blackboard visible to you?
Yes, sir.
Yes, sir.
ठीक है। ओके, सो इन केस कोई भी स्टूडेंट अगर आपको पिंग करता है कि मैं ज्वाइन नहीं कर पा रहा, तो मैंने यहाँ से इनेबल वेटिंग रूम डिसेबल कर दिया है। और वो ज्वाइन जब भी वो लिंक पे क्लिक करेगा तो कुछ टाइम लगेगा, 1-2 मिनट, उसके बाद वो एंटर हो जाएगा। मैंने यहाँ से कोई रेस्ट्रिक्शन अभी रखा नहीं है, एक्सेप्ट कि आप लोग अपने आप को म्यूट और चैट नहीं कर सकते। हैंड रेज करिए, फिर हम डिस्कस करेंगे। ओके, सो so yesterday we have seen the characteristics of a real PN junction diode, and this was the equation that represents the current when the diode is in forward bias condition. You can also calculate current when the diode is in reverse bias. Okay, in reverse bias, let's say that VD is -10. So if you will put -10 here, so you will have ID equal to IS e raised to power -10 divided by eta Vt minus 1. So e raised to power -10. So you have Is into e raised to power -10 divided by eta Vt minus Is. So this will be a very small quantity because you are calculating e raised to power -10. So this will, we can approximate it to 0. So you will have Id is equal to minus Is. So mathematically, when the diode is in reverse bias, the diode current will be always Is, minus of Is, that is flowing from P side, N side to P side. Otherwise, in forward bias, you have Id equal to Is, e raised to power Vd divided by eta Vt minus 1. So your Is is reverse saturation current. Vd is voltage drop on the diode, not the external voltage drop across on the diode. Eta is the ideality factor. For ideal diode, it is 1 for ideal diode. And generally its value lies between 1 and 2. Okay. Vt is thermal voltage, that is given by the formula Kt by Q. So K is Boltzmann constant. So its value is 1.38 into 10 to the power minus 23 joules per Kelvin. And T is temperature in Kelvin. So that can be calculated by 273 plus temperature in degree Celsius. And Q is 1.6 into 10 to the power minus 19 Coulomb. Okay, so you have to use this formula in the starting questions of TUT. I think it is a TUT 1. So this formula was to be used in the question number 1 and 2 of TUT 1. Then this is the IV characteristics graphic. We are representing IV characteristics of real diode graphically. So this first quadrant is representing the forward bias region, and the third quadrant, this is representing the reverse bias region. So in the first quadrant, when the diode is in forward bias region, you can see that up to a certain voltage that we called as knee voltage or on voltage or pinch off voltage, up to this, the current ID is very, very small. And after that, VD is fixed, voltage drop across diode. This is voltage drop across diode. So this is not changing. Okay, the variation is very, very small. And this current is increasing drastically. So this is your experiment number. I think this is experiment number 2, where you have to measure the IV characteristics of a diode. So you will be whenever you will be plotting your reading on a graph, so you will be having some this kind of characteristic. Okay, so you can see that you will be uh, seeing that the value of this knee voltage will be somewhat around zero point 0.5 to 0.7 volt in between. VD will not vary much. It will from zero point 0.5 onwards, it will vary very slowly, and it will try to reach zero point 0.7. Okay, so this thing you can verify experimentally. Experiment number 2. And in reverse bias, the current, this is reverse saturation current. This is denoted by IS. So it is of order of picoampere or nanoampere, very small value. So it is almost, we consider this as almost constant. And whenever you increase the external voltage in the negative directions, so that much amount of voltage is being dropped on the diode. So this is representing that, and at this point, that is denoted by V subscript BV. So VBV is breakdown voltage. Okay, and after that, I after BV, I is very high, and because of that, enormous amount of heat will generate, and that will burn your damage. So your diode will damage permanently. Okay, so avoid. You have to avoid increasing the voltage after VBV. So whenever you are doing practicals, don't increase reverse voltage beyond this BV. So that values will be given to you. That is like 50 volts. For some diode, it is 100 volt. That depends. So important point to be noted in forward bias region is that knee voltage is the minimum voltage to turn on the diode. Okay, even your real diode is in forward bias. It doesn't mean that it will be on instantly. Just you increase the you increase the V slightly, and you will start getting ID. This is not the case with real diode. So you have to increase your external voltage beyond the knee voltage. Okay, below the knee voltage, diode is literally off. It is like off. So this value of ID, that will be very close to 0. So we approximate it to 0. And this the value of the knee voltage for silicon is zero point 0.7 volt, and for germanium is zero point 0.3 volts. So if you are having this kind of configuration, okay, so this is V, this is, suppose this is silicon diode, and this is some resistance R. So if the value of V is, let's say, 0.4 volt, so your diode will be practically in off condition, even though you have plus at P terminal, minus at N terminal. But this 0.4 is less than 0.7. So you will consider that your diode is in off condition, and you will replace it by an open circuit. Off, diode off means open circuit, infinite resistance. Okay, so we will see what will happen if this V is, let's say, 10. So we will see shortly. We will see for the greater values what should be done, what should be the equivalent circuit. Yes, Mayank. हाँ मयंक.
सर मेरे को डाउट था एक।
पूछो.
सर ये जो अभी हमने वो रिलेशन पढ़ा आईडी और आईएस के बीच में, रिवर्स सैचुरेशन करंट के बीच में, तो सर वो हम फॉरवर्ड बायस में यूज करेंगे या रिवर्स बायस में?
मैंने रिवर्स में भी तो बताया था आपको, रिवर्स में भी देखो, रिवर्स में भी तो कर सकते हैं उसको। ये रिवर्स में -10, तो e⁻−10, e की वैल्यू 2.73 समथिंग होती है, और फर्दर उसको हम डिवाइड कर रहे हैं इटा बीटी से, तो समथिंग वेरी स्मॉल पॉइंट, समथिंग लाइक 0.0000001 लाइक दिस। ओके, सो यू कैन इग्नोर इट, यू कैन कंसिडर इट जीरो। सो जब आप उसको जीरो करोगे तो आपके पास ये रह जाएगा, दिस टर्म इज जीरो, दिस इज -vs, सो आईडी इज इक्वल टू -is, तो वो आईडी हमेशा -is ही रहेगा मैथमेटिकली सॉल्व करने जाओगे तो। सो यू कैन
सर सर इधर आईएस रिवर्स सैचुरेशन करंट है, तो फॉरवर्ड बायस में भी होगा ये?
हाँ, ये डेरिवेशन मैंने is दैट मल्टीप्लाइड बाय दिस थिंग, ये फॉरवर्ड बायस में होगा, बट ये इस फैक्टर से e रेज टू पावर दिस फैक्टर से मल्टीप्लाइड होगा। और is डिपेंड करता है आपके डोपिंग कंसंट्रेशन पे, इंट्रिंसिक कंसंट्रेशन पे, विड्थ ऑफ डिप्लीशन रीजन पे, डाइलेक्ट्रिक मटेरियल कौन सा यूज कर रहे हो, सिलिकॉन है, जर्मेनियम है, डाइलेक्ट्रिक, बहुत सारे फैक्टर होते हैं, तो बड़ा कॉम्प्लेक्स सा डेरिवेशन है, उस पे हम नहीं जाएंगे अभी।
सर तो ये रिवर्स सैचुरेशन करंट वही होता है ना जो डिप्लीशन रीजन में होता है?
डिप्लीशन रीजन में वो तो पूरे डायोड के अक्रॉस ही होता है, डिप्लीशन रीजन भी तो डायोड का पार्ट है, तो करंट अगर फ्लो करेगा तो वो ऐसे ही तो फ्लो करेगा।
यस सर, यस सर।
वो डिप्लीशन
ओके
रीजन तो हमेशा रहेगा, चाहे फॉरवर्ड बायस हो या रिवर्स बायस हो, ये रिवर्स बायस में होता है माइनॉरिटी चार्ज कैरियर की वजह से।
ओके
ठीक है,
सर।
ओके। Okay, so this is the graphical representation of IV characteristics of real diode. And now we can make a comparison between ideal characteristic and practical characteristics. So this green line is representing the IV characteristics of a ideal diode. This is for ideal diode. Okay, so voltage drop across this diode is zero. You can see for ideal diode, when it is in forward bias, means plus at P minus at N, we replace this diode by a short circuit or a simple wire. And resistance we consider that it is having zero resistance, okay, because Vd will be zero, this voltage drop will be zero. Now these are connected via same wire, so Vd is zero, so 0 divided by I, this I is controlled by the external resistance, I have already shown you. So Rf is zero, forward resistance is zero. So zero voltage drop, no voltage drop, but some value of current I that depends on external resistance. And when your diode is in reverse bias, means minus at P terminal and plus at N terminal. So we replace this via open circuit, because this is behaving like infinite resistance. We can prove that R is V by zero. Zero means zero current. Current cannot flow through it. So practically, sorry, ideally its value is infinite in reverse bias. So current is zero no matter how much you increase the voltage. If this is the configuration, something like this, suppose this is your diode, even though you have connected external resistance, and this is the value of V, so this plus minus Vd, so Vd will be exactly equal to minus V. So now if this V is -10, so voltage drop across the diode will be -10. If this value of V is -5, so voltage drop across the diode is -5. That depends. So Vd will be exactly equal to minus V, except for this point VBV. So this is the region of operation in reverse bias, and this is okay. And this red line is representing the characteristics of practical diode. Right now that we have discussed in the previous slide. Okay, so this is the difference: real ideal diode, practical diode. Okay, so we have considered that ideal diode is having zero resistance in forward bias, infinite resistance in reverse bias. So what should be the resistance of the real diode? Okay, this is not be the practical diode is not behaving like this. So this means it is having some value of V. Let's say at this point, it is having some value of V. and correspondingly it has some I. So this means that it is having some resistance. It is exhibiting some resistance. It is resisting the flow of current. So what is that resistance? That we will see. So for diode, we define three types of resistance. First is DC resistance. Second is AC resistance. DC means direct current resistance. AC is alternating current resistance. And third one is average resistance. That we will see one by one. And this is the part of again tute. I think tute number 2. Question 3, 4, 5. Remaining questions is based on the resistance values. So that we will see one by one. Before that, we will be discussing the temperature effects, because you know that in our India there is a huge variation of temperature. Minimum can be, let's say, 20 degrees Celsius. Maximum can be around 35. Sometimes it is 40. So temperature varies a lot. Okay. So what is the effect of this variation in temperature on the characteristics of diode? Okay. So this is the graph taken from the Boylsted book, and this blue line is showing the curve for a silicon diode. You can see silicon diode at room temperature. So generally room temperature is considered equal to 25 degrees Celsius. Okay, even 25 to 27, that much you considered as room temperature. But absolute value is taken as, in some book they take 25 degree as room temperature. In some other literature they take 27. Okay, so that doesn't make much difference. So in Boylsted, they have taken 25 degrees Celsius as room temperature. So this is the curve. So suppose your surrounding temperature is 25 and you are using your PN junction silicon diode. So this will be the curve. Okay. Now, what is the effect of temperature? So in forward bias region, the characteristics of silicon diode shifts to the left. So if this is the characteristics at room temperature, and if temperature increases, this characteristics will shift to left direction at a rate of 2.5 millivolt per centigrade degree. Okay, so you can see this is the characteristics left to this blue one, characteristics, IV characteristics shown in a dotted line, and it is showing 125 degrees Celsius. Okay, so this was 25. This is for 125. So increase in temperature is 125 minus 25, that is 100 degrees Celsius. So suppose that temperature increases to 125 degrees Celsius. So from 25 degrees Celsius, the new temperature is now 125 degrees Celsius. So the difference is of 100. And it is saying that it will shift to left at a rate of 2.5 millivolt per centigrade degree. So for 1 degree change in temperature, the left shift will be 2.5 millivolts. So for 100 degrees Celsius increase in temperature, the left shift will be 100 degree into 2.5. Okay, because it is a left shift, so I will put a minus sign here. So that will give you minus 0.35 volt. So this curve, the relative difference between the blue and this dotted line on left is 0.35 volt. Okay, now each and every value, each point is shifted by 0.35 volt. Your knee voltage will be also updated to 0.7 minus this 0.35 volt. So this will be the new knee voltage value, 0.7 minus 0.35 volt. Okay, and okay, so if you carefully observe this, what does it mean? It means that for the same amount of voltage drop, you are now having comparatively higher value of current. These are two. Let's take these 2 points. Let's take this VD. So you have, let me change the color. So this line, and for the same VD at 125 degrees Celsius, we have this line. So at 25 degrees Celsius, I am having this value of current, I1. At 125 degrees Celsius for the same VD, I am having I2, and I2 is greater than I1. Okay, so can anyone tell why this is happening? कोई guess क्यों ऐसा हो रहा होगा? Okay, so reason is that thermal generation. The reason is थर्मल जनरेशन, जिसको अभी तक हमने इग्नोर किया था. हमने ये माना था कि जो भी डोनर और एक्सेप्टर एटम जिसने जितना फ्री चार्ज कैरियर दे दिया वही कंट्रीब्यूट कर रहे हैं. एंड थर्मल जनरेशन की वजह से इलेक्ट्रॉन होल पेयर नेग्लिजिबल है. बट आप अगर टेम्परेचर को बहुत ज्यादा बढ़ा दोगे तो बहुत ज्यादा वाइब्रेशंस होंगे बॉन्ड्स के बीच में, और बहुत ज्यादा बॉन्ड ब्रेक होंगे. उसकी वजह से उतनी ही क्वांटिटी में फ्री इलेक्ट्रॉन्स और होल्स जनरेट होंगे, और वो क्वांटिटी इतनी होगी कि वो मैच करेगी डोनर और एक्सेप्टर एटम्स की कंसंट्रेशन को. तो उसको अब हम इग्नोर नहीं कर सकते, और उसकी वजह से हमें करंट इंक्रीज इन करंट मिलेगा. दिस इज द रीजन. ओके, एंड सिमिलरली इफ देयर इज एन डिक्रीज इन टेम्परेचर. ओके, ये तो इसने तो इस डेफिनेशन के अकॉर्डिंग तो इंक्रीज इन टेम्परेचर पे करंट इंक्रीज होगा, लेफ्ट शिफ्ट होगा. इफ देयर इज एन डिक्रीज इन टेम्परेचर, so this line, dotted line on the right, this is the characteristic at minus 75 degrees Celsius. So 25, earlier it was 25, now it is minus 75. So the change is 25 minus of minus 75, that is 100 degree. But this time this 100 degree, this is decrease, this is 100 degree decrease. Okay, so the graph will shift to the right side. The graph will shift, this IV curve will shift to the right side by the same rate. So again, the change is 100 degrees Celsius. 100 multiplied by this 2.5 will give you, now you have to take plus 2.5, right side shift ho raha hai. So 100 into plus 2.5 millivolt, this is millivolt, 10 to the power minus 3 volt. So that will give you 0.35 volt. Okay, so it is obvious, if the temperature will decrease, the thermal generation will also decrease. Okay, तो थर्मल जनरेशन डिक्रीज होगा तो उसकी वजह से जो भी करंट आ रहा है वो कम होते जाएगा. तो आपको अब यहाँ पे सेम वैल्यू के लिए अब आपको ज्यादा वोल्टेज देना पड़ेगा, ज्यादा करंट के लिए ज्यादा वोल्टेज देना पड़ेगा, आपको ज्यादा एक्सटर्नल इलेक्ट्रिक फील्ड सप्लाई करनी पड़ेगी. सो दिस इज द रीजन. सो दिस वाज अबाउट this was the shift in characteristics in forward bias. Okay, reverse bias में क्या होगा? In reverse bias region, the reverse current IS doubles for every 10 degree rise in temperature. Okay, so let's say that at 25 degrees Celsius at room temperature it was IS. So if you increase the temperature by 10 degree, if the new temperature is 35 degrees Celsius, so the new value of IS, the new value of saturation current will be double, that is 2 into IS. Okay, now you again increase the temperature by 10 degrees Celsius. So the now new temperature is 45. So the new value of IS will be 2 times of this. At 35 degrees Celsius, you have 2 into IS. So at 45 degrees Celsius, you have 4 into IS. Okay, so you can have a mathematical formula for this. Sometimes it is asked in objective questions. So let me erase this first. So in reverse bias, let's say that IS old is the value, IS old is the value of saturation current at temperature T old, and IS new is the value of saturation current at some new temperature. So IS new is given by IS old 2 raised to power T new minus T old divided by 10. So this is the formula that you can use. Now you can use this for any temperature change. T new, T old can be any temperature. It is not mandatory to have a 10 degree rise. You can have a 5 degree rise 6 degree rise, any value. So using this formula, you can calculate the new value of reverse saturation current at the new given temperature. Okay, so let's say that T new was 35, and you have I 35. Sorry, T new. Let's say that T new is 35, T old is 25. So I at 35 will be given by I at 25. 2 raised to power 35 minus 25 gives you 10. 10 divided by 10. So 2 into I of 25. Okay, so value doubles. So this formula is valid. Now we will move to the resistance values, resistance level of real diodes. So like I said that three types of resistance are defined. First is uh, DC or static resistance. Okay, so it is defined by this DC resistance, symbol is R subscript capital D, and this is the ratio of VD by ID. So this VD, this is the VD, and correspondingly we have some ID. So just you have to take VD and ID. And this point is known as quiescent point, Q point. Quiescent means still, रुका हुआ. So this Q point is known as DC operating point. Okay. So these are the possible values of voltage drop across the diode, starting from 0 to some value VD. Okay, but in actual, you will be working on only one point. Let's say it is VD. It may be 0.5 volt, or it may be 0.6 volt, or it may be 0.7 वोल्ट. आप एक्चुअली में एक ही काम पे, एक ही वैल्यू पे ऑपरेट करोगे उसको, है ना. हमारे मोबाइल में एक ही बैटरी होती है 3.7 वोल्ट की. हम उसका एनालिसिस 0 से 100 वोल्ट के लिए कर सकते हैं, बट हमें लगा कि 3.7 पे बेस्ट है, तो हमने 3.7 वोल्ट का बैटरी यूज किया. तो उसी तरह से दिस इज गिविंग ऑल द पॉसिबल वैल्यूज ऑफ वीडी वर्सेस आईडी, बट वी विल बी ऑपरेटिंग एट अ सिंगल वैल्यू. एक ही हम उसमें डीसी बैटरी लगाएंगे, एक ही वैल्यू दे सकता है वो. तो लेट्स से दैट because of that value, the voltage drop across diode is VD and the current is ID. So the ratio of that VD by ID is RD. Okay, let's say that this is VD1, ID1. So RD1 is VD1 by ID1. So this is at point 1. This was at point 1. Let's say at this point, this is at point 2. So we have VD2 here, ID2 here. So it was at point 1. Okay, at different point, we will have a different value of resistance. So at point 2, we have RD2. Now because VD and ID has changed, so we have VD2 divided by ID2. Okay, so in forward bias region, DC resistance below knee voltage will be higher as compared to voltage above knee, because RD is VD by ID. So below knee voltage, this ID will be very less, of the order of pico and microamperes. So this ID will be, this RD will be very high below this knee voltage. Low value of VD, low value of ID because of this. Okay, now after knee voltage, more value of current, less value of RD. Okay, so you can see that more the value of current, less will be the value of RD. So ID, comparing these two values, RD1, RD2. Okay, so there VD1 and VD2, there will be not much difference. Okay, the difference between VD2 and VD1 will be of order of 0.02. The second decimal place will affect. Okay, whenever you will do practical, you will see that second or third decimal places change in this region. So VD will be not VD2 and VD1 will not vary too much, but ID1 and ID2 will vary by a huge difference. So ID2 will be very much greater than ID1. Hence, RD2 will be obviously less than RD1. So the reason is that high amount of current is flowing by a very little increase in voltage. Okay, so it is obvious that resistance will decrease. So uh, more value of current flow, less value of RD. Okay, and less value of current flow, more value of RD. That is the case. And in reverse bias, RD is given by the same formula, that is the ratio of VD by ID. ID is again of the order of picoampere or nanoampere. So if I take the ratio RD 10 divided by 10 is to power picoampere, let's say minus 12 ohm. So I will be having 10 to power 11 ohm. Okay, something like this. So I can consider it as infinite because I will be using a resistance like 1K or 10K in my circuit. So compared to this 10K, 10 is to power 11 can be approximated to infinite. So in reverse bias, you have to again and again approximate it to infinite always. Okay, you have to carefully observe, you have to carefully calculate in forward bias. So this was the question number 3, I think 3 of tube 1. You have to just use this formula for given value of VD divided by ID. RD will come. That's it. Next is AC resistance, and that is also known as dynamic resistance. Okay, so I have drawn one circuit with one DC source. Okay, so we have given a DC source, and a AC source is superimposed on it. So an AC source is in series with DC source. So we say that AC source is superimposed on DC source, and then diode is connected. So now this across this diode, we have DC voltage, a constant voltage, plus AC. Let's imagine that this AC is a sine wave, so a sine wave like this. And one more constraint is there: the magnitude of this sine wave, the magnitude of this voltage is very, very small. It is a very small AC signal. Okay, of the order of of the order of 10 millivolt or 20 millivolt, of the order of this millivolt. So if this is the case, we have one DC signal and one AC signal of this order is superimposed on this is superimposed on this diode. So in that case, we calculate AC resistance. Okay, so this is again the Q point. This Q point is defined by this DC signal. Whatever the value of VD, because of this DC voltage, we will be having some value VD. Okay, and we have now superimposed AC signal. So because of this AC signal, current will fluctuate for half cycle in positive direction, for the remaining half cycle in negative direction. Okay, so this is the range in which current will vary, and accordingly voltage will also vary. Okay, so this is the minimum point I1, this is the maximum point I2, and correspondingly we have V1, V2. Okay, and you can calculate it by applying superposition theorem, that we will also do, but not in this lecture. So you will be given some DC values and AC values. You will have to calculate the overall current. So we can apply superposition theorem. Means first we will consider DC, we will completely ignore AC, then we will perform calculation. After that we will ignore DC, we will consider purely AC, then we will again perform the calculation, and then we can add the two results. That is what superposition theorem. So that can be applied here. Okay. Anyways, we will do it later on. At this point, we have to define RAC. So RAC, the symbol for AC resistance, that is nothing but delta VD by delta ID. Again, saying this is for very small values of AC signal. Okay. So for very small differences, RAC can be calculated by deriving del VD by del ID. So instead of calculating this, why not we calculate the derivative, that is del VD by del ID. And 1 by, okay, so this will be the value of RAC, and 1 by RAC is equal to del ID by del VD. So del ID by del VD is nothing but slope of the tangent at point Q. So if these values are very small, this I2 minus I1 is very small, correspondingly V2 minus V1 will be very small. So it is like measuring the slope of the tangent across this Q point, slope of this tangent. So this is nothing but 1 by RC. Ohm's law में भी तो वही होता है. So this is V, this is R, sorry, this is I. So 1 by R is slope. So this 1 by RAC is slope at this point. If you draw the tangent to this curve at this point, so the slope is 1 by RAC. That is given by del ID by del VD. Okay, now we will derive this, the formula. What is the actual value of RAC? So we know that RAC is given by IS e raised to power VD by eta VT minus 1. Now taking derivative del ID by del VT on the both the sides. So del ID by del VD, del ID by del VD in the bracket. I have written this equation as it is. And now if you will open the bracket, so you have IS e raised to power VD by eta VT as it is. And that power term, okay, we are differentiating with respect to VD. So this VD divided by eta VT. So we will have eta VT in denominator. And this is minus IS. So constant derivative of constant is 0. Okay, so from now this equation, you can see that ID is IS e raised to power VD by eta VT minus IS. So we have this term numerator. This is similar to this term. So this term can be written as e raised to power VD by eta VT can be written as ID plus IS, taking IS to left hand side. So I have written this term as ID plus IS, and in denominator I have eta VT as it is. Okay, now IS is very small. ID is very greater than as compared to IS. So I am again approximating it. We have to make many times we have to make certain approximation for simplicity. So this thing is approximated as ID by eta VT. Okay, and this will be the value of 1 by RAC. Okay, that's what we have defined in the previous slide. We have 1 by RAC. So RAC is reversing this del VD by del ID, eta VT by ID. Okay, so now for eta equal to 1, let's say that our diode is ideal, eta is 1, and we are operating our diode at room temperature. So that is 25 degrees Celsius. So the value of Veta that can be calculated by KT by Q. So take this T as 273 plus 25. Put the value of K and Q. So the result will be 26 millivolt. So RAC is 26 millivolt divided by ID. So at room temperature, you don't have to even calculate the other values. Just calculate ID by using this formula and substitute the value of ID. So you will have the value of RAC as 26 millivolt divided by ID. That's it. So you have to remember this formula. Okay, so this is the how we calculate the AC resistance. We have one more resistance, that is average resistance, but uh, we are we have extended our lecture by 1 minute, so I have to now end here. So in the next lecture, that is on Friday, I will take some doubts. Till now, if you are having some doubts, we will be taking that doubt first, and then we will be starting with AC resistance. अक्षित आयुष आपका डाउट मैं बेशक लूंगा, बट फ्राइडे को है ना, प्लीज अभी मुझे वो करना है, दूसरा टीचर वेट कर रहा है, तो हम डाउट से शुरुआत करेंगे फ्राइडे वाली क्लास में. ओके, हैव अ नाइस डे, सी यू ऑन फ्राइडे.